All right, and let's just talk about time. When are you thinking? Actually, are you on time, or how are we doing on time?
Yeah, we will on time. Yeah.
Okay.
Okay, thank you, Zitao. All right, can you see my screen?
We can.
Yeah, we can.
Okay. Hi, I'm Goi. I'm a colleague of Zitao, so I'm also with TAL AI team. Today, I want to talk specifically about representation learning in education domain. Oh, should I just go to the full screen side mode?
You certainly could.
It's better.
There you go.
Good.
We can see your screen well now in full presentation mode.
Yeah. So what is representation of data? So I think representation learning is basically you want to map some raw features into a latent space. And maybe in that latent space, the representation of data would be more robust. So if you just train your model in that latent space, the task would be easier. So let's take a look at this example on the left side. Let's say we want to do a binary classification on this raw input. Instead of directly training a classifier on the raw input, we could first map it into a latent space, like maybe a 100-dimensional hidden state. And then we want in this space such that the positive examples, they are close to each other in a cluster, and positive and negative examples, they are like far away from each other. So the decision boundary will be clear. So if we later train a classifier in this latent space, the classification task would be easier. Also, just graph embedding has also been very popular in recent years. So on the right side, we have a map of Wikipedia. We can also apply like such a representation learning algorithm to get representation of nodes and edges. And then we can just do some traditional machine learning algorithm on the learned embeddings. All right. So the situation is the same in educational scenarios. So for educational data, we have all different forms of data that come in various sources, such as online class videos, questions, textbooks, conversations, homework, handwritings. Still, we can use representation to get a unified kind of embeddings, and then we can train our machine learning algorithms on it. Next, I will talk specifically about how to learn from limited and inconsistent data. So there are many two challenges that prevent us from learning a robust representation. The first challenge is that we have small data. The second one is that we have noises, inconsistencies in our crowdsourced data. So just as Zitao mentioned, in general, I think educational data, there are lots of educational data. Like every day we have millions of like online classes going on, and we have thousands of homework being graded and submitted. But why we still have limited data? The first could be some privacy issues. Maybe students don't want their assignments to be recorded. Maybe some teachers, they don't want their classes to be videotaped. So we actually don't have access to this data. And the second reason could be that labeling educational data is really subjective and much harder than some traditional tasks, such as labeling images. So for example, I'll give you a very quick example. So let's say we want to build an online class quality judger. So to do that, we need a lot of class quality labels. However, just normal people couldn't label these classes because it requires years of teaching experience. And also, on the other hand, you have to watch the entire classes, which may be 1 or 2 hours long before you can make a conclusion. So it all makes labeling educational data very expensive. That gives us small data. So how do we deal with small data? Mainly there are two approaches. One is model-wise, the other is data-wise. So for model-wise approaches, basically we want to transfer or reuse some previous learned knowledge and generalize that knowledge to our target task. For example, in recent years, the very famous BERT model in NLP, they are pre-trained on two pre-trained tasks, language modeling and also next sentence prediction. So in this pre-training stage, the model just kind of learns some common senses about languages. And then we can generalize that knowledge to other tasks such as text classification, question answering, and so on. And sometimes it's also very useful to just utilize some expertise. So we inject some extra knowledge into our model for better performance. We can just maybe put some domain expertise priors or introduce knowledge graphs into our model. And for the data-wise, usually we apply data augmentation to obtain a larger and better training set. So next, I want to talk about the differences between three ways to transfer knowledge. One is the transfer learning. So for transfer learning, there's only one source task and one target task. They are different, but they share some similarities. For example, let's say the source task is that we want to evaluate the speaking fluency of women's voice. And the target task could be to evaluate the fluency of men's voice. So they're kind of different, but they share similarities. So in that guarantees that we can reuse the knowledge from the source task. And for multi-learning tasks, really the difference is that we have multiple tasks going on. So the model is trained on this multiple tasks jointly to capture their intrinsic dependencies. And for meta-learning, that we train our model on multiple tasks and to generate that knowledge to unseen to a new task. But sometimes it's actually much faster to just incorporate prior knowledge. Let's say, for example, in this picture, we want to predict the probability of heart failure given patient's history and symptoms descriptions. So let's say this doctor, this expert told us that a high blood pressure and arterial disease, there are two key factors. So to build our model, we could simply just put very positive priors on these two factors, and that could make the model more robust. So in the last few slides, I talk about how to deal with small data issue from the point of model. So actually, we could also think about this problem from the point of data. So how do we do data augmentation? Usually, we can use some handcrafted rule or just apply augmentation strategies to get more data. So in my practice, I used to build a English grammar correction model. So the model can take some sentences with errors and returns a sentence that has been corrected. So to do that, we need lots of sentences with grammatical errors. And one rule is that we can randomly delete or insert or just shuffle some characters to generate errors. And recently, generative model has also been very popular. So I've already seen that generative models such as GAN has been applied in CV to generate very realistic images. However, the reality is usually that in your data, only a small portion of the data is labeled. So still lots of data, they are still unlabeled. If you want to take advantage of both, you may use this so-called semi-supervised learning. So for example, I can just train my classifying model on the labeled data and then make predictions on all my unlabeled data. And then I select those unlabeled data that fall close to the decision boundaries. And then I can introduce crowdsourcing to get those unlabeled data, the label of those unlabeled data, and append them to our training data set. And that just boosts the overall performance. Okay, I've introduced the small data problem and how do we deal with that. Next, I will talk about the inconsistency of crowdsourced data. So this simple example, let's look at this picture. So it has, it says KDD2020 with 2 sailboats and ocean. And if we just show this picture to our crowdsourced workers and ask them where was KDD2020 planned to hold, as you can see, they give very conflicting answers because this question is really hard, given that San Francisco and San Diego, they are both seaside cities. So how do you really find the true answer? How do we find the true label of the task? This is called choose inference. And by definition, choose inference means that given different task answers collected from workers, the target is really to infer the truth of different tasks. So there are a very simple solution is to take the answer that is voted by the majority of the workers. This is called majority vote. But majority vote actually treats each worker equally. So it doesn't consider the diversity quality for each worker. This is especially, it has limitations, especially when your worker, they vary in their expertise. And to solve that problem in 2009, and Whitehill, they introduced a model called GLAD. So in this model, both the difficulty of the object and the expertise of the laborers, they're both considered to model the probability of the observed labels. So if you take this formula, let's say I means the ith worker, and alpha I just means that the labeler accuracy of the ith worker. And beta means the difficulty of the task. Beta J actually indicates the task difficulty of the J's images. So if a task is easy and the labeler is very accurate, the probability of the observed label is very high. Okay, I've introduced a few approaches to deal with small data, but still, we still might have very few trainable labels. And next, I will talk about a novel framework called RLL. This work was published in ICDE by TAL team. So the first part of RLL is called the grouping-based architecture. Really, this is really just to deal with the small data problem. Let's use this example, the classification as our example again. Let's say we still have very limited data. We have M positive and N negative data on the left side. And if we just directly training our classifier on this limited data, the performance isn't really good. So instead of doing that, and how do we just increase the size of our training data? We could do grouping. So on the right side, we can select 2 positive examples in blue and K negative examples in red. We group them together to form groups. And later I will show how do we feed this group into a neural network to train to get a robust representation. What I really want to say is that by this grouping architecture, we can get substantially more data. Now we already have a large training group data sets. Next, we need to consider how to reduce the negative impacts of noisy crowdsourced labels. So how do we deal with inconsistency? So still, let's say we have example A and example B here, and we ask 5 workers to label them, either as positive or negative. So you see example A has 3 positive out of 5 workers. Example B has 5 positive votes. So obviously we are confident to say that example B is very positive, but we are not sure about the true label of example A. So they should be treated differently in our model training. And based on this intuition, we want to give each data a confidence score and treat this confidence score as a random variable. So one way to treat the confidence score as a random variable is that we can use maximum likelihood estimation. According to MLE, so example A would have the sum of all the positive votes for example A would be 3, and divided by 5 workers. So the score of example A would be 3 divided by 5 is 0.6, and example B would have a score equals to 5 divided by 5, which is 1. However, MLE has limitations, especially when the number of workers is very small. So to better infer the true labels, we can actually introduce some Bayesian priors into the calculation of this confidence score. So here, we can introduce alpha and beta as our label class priors. Okay, now for RL, we already have a large training data sets and confidence score estimators. So the third part is really how do we do model training? So on the left side of this graph, we feed all the groups into a neural network to do nonlinear projections. And through projection, we can get their embedding in the latent space. And then on the right side, the loss function is really, we want to maximize the probability of retrieving a positive example, xj, given another positive example, xi, together with k negative examples. So in other words, we want in our latent space that all the positive examples to be close to each other, and positive and negative examples to be far away from each other. And also to deal with inconsistency, we also integrate confidence score into the loss function, such that examples with inconsistent labels contribute less to the loss, and examples with confident labels contribute more to the loss. So as I introduced, in RL, the grouping are done with random strategy. So we just random pick up positive and negative examples together. However, this is not the most efficient way to create groups, because maybe in our data sets, maybe some data, their distribution are easy to capture. So we don't want them to repeat our training groups again and again. So this year, we actually introduced a hard example mining strategy into RLL. So hard example mining strategy is iterative algorithm. At iteration T, we first make predictions on the validation sets using current learned embeddings. And then since we know all the labels for the validation sets, we could find those mispredicted examples in the validation sets. Let's call them just validation hard examples. Then we want to find the most similar examples to these hard validation examples from the training sets. This can be done using various distance metrics, such as Euclidean distance, cosine similarity, L1, L2, and etc. And finally, for the next iteration, T+1, we form groups with these training hard examples. And this helps the model to converge faster and obtain robust representations. But besides hard example mining strategy, we can actually use a sampling network to select examples before grouping. So this work is called hard example while sampling network. So it has 3 steps. In step 1, we decide if an example is a safe one based on its crowdsourced labels and embeddings in the latent space. In step 2, we generate a robust anchor for each group. And finally, in step 3, we utilize a sampling network to help us select those hard examples from all the possible training groups. I will talk about them in details later. So here, I will explain what is a safe and unsafe example. So let's see this example on the left side. So on the top, this example has 6 positive votes out of 7 annotators. So we still need to compute the confidence score, which is 6 minus 3.5 divided by 3.5, which is 5 over 7. So I can say that this one is a very confident example, is a safe one. But for the second example below, it has only 4 votes out of 7 annotators. So the confidence score goes down to 1 over 7. And how do we decide if an example is safe? We need to go to the latent space. So actually the idea is that for any example in the latent space, we want to look at its neighbors. So if the neighbors, the majority of the neighbors, they have a class label different from the example studied, we think this one is an unsafe one. So for example, on the right side, on the top, this blue one is a negative, but all its neighbors, there are positive examples. So we believe that this blue one is unsafe. However, the example below is actually very safe because all of this 5 examples, there are negative ones. And later when we form groups, the safe examples will have a higher probability to be selected, but the unsafe example will have a low probability to be selected in our training groups. And next, we want to get a robust anchor for each training groups, because we are still worried that there might be some ambiguous anchors in our training groups. So that may harm the model, and we want to get rid of them. So how do we do that? The intuition is that we believe the overall average is much safer than any individual sample. So to reduce the influence of ambiguous anchors, and anchors within a batch are replaced with a robust anchor. The robust anchor is the weighted average of the original anchors by their confidence score, as shown by this formula on the right side. And the final step of this framework is the sampling network. Different from the hard example mining strategy I introduced before, we introduce a sampling network to help us select the hard examples. So we define this hardness as that for any group, if it contributes a lot of, if its contribution to the loss function is large, we think this is a hard group. So we train such sampling network as a supervised model. And the model just take groups as input and predict the hardness of this group. And later for the next iteration, we use this sampling network to rank all the possible groups. And we take only the groups with very high hardness scores and take them into the training groups for the next iteration. Okay, I think that's all my introduction, and I will pause here for any questions.
I just want to say, actually, that seems like some really important work. Actually, I'm glad to learn about it. And I saw how you were citing Jacob Whitehill's GLAD actually algorithm. Jacob works with me at WPI.
Okay.
I definitely need to learn about, actually, your technique seems really cool, since I'm actually going to talk all about crowdsourcing. It seems like actually I need to really comprehend actually your work, because it seems really important. There's not a question in there, it's more just a compliment.
Thank you so much. Any other questions? Okay, if no other question, I will stop sharing. And next, let's invite Haoyang, my colleagues, to introduce the learning from multiple modality.
Okay, thank you, Guowei, and I will share my screen.